Okay, we are going to talk about domain, range, and end behavior today. So when we talk about the domain refers to all of the x values, whereas the range refers to the y values. So this tells us where the graph of the function belongs on our coordinate plane. When we write the answers for domain and range, we use two different types of notation, either interval notation or inequality notation. For interval notation, we use brackets and parentheses. So brackets are like this, very boxy. Parentheses are the rounded version of that. For the inequality notation, we use less than or equal to, greater than, and greater than or equal to. So for the problems below, we're going to graph the polynomial using a table. Then we're going to state the domain, the range, and the end behavior of the functions. So I've already got this graphed over on Desmos. So let me open up Desmos here. Whoa. So I graphed my function and then I created a table in Desmos. And if you don't know how to create a table in Desmos, you just click on the setting button. And then for whatever function, that little table is what you click and it will auto-generate a table for you. So I'm going to split view my screen so that I can see the questions as well as my table and graph here. So looking at this function, just the function itself, it's got a 3 for the degree and a -1 for the leading coefficient, meaning that this is an odd negative function, which we can see based on my graph. It's following that pattern of starting high and ending low as I move left to right on the graph. What I want to do here is I want to recreate this table because it's going to help me when I go to graph it on my paper here. So I've got -2, 20, -1, 4, 0, 0, 1, 2, 2, 4, 3, 0, and 4, -16. So I'm just recreating that table on my paper so that it's easier to graph. And then I am going to draw this graph just so that I can reference it without having to have Desmos pulled up on this side over here as well. So we've got, we can't really graph -2, 20. So the first point I'm going to graph is -1, 4, 2, 3, 4, and then 0, 0, 1, 2, 2, 4, 3, 0, and I can't graph 4, -16. So the graph of this function looks a little something like this. Now my last step here was to determine the domain, range, and the end behavior. So fun fact for polynomial functions, the domain is pretty much always going to be all real numbers. Very rarely are you going to see anything that's a polynomial that is not going to have a domain that is all real numbers. And all this means is that I can plug any number in for x and it's going to spit out an answer. Any number I plug in for x, that's going to give me an answer. So here's how we write this. We can say all real numbers by doing a fancy R, which is just a capital letter R with a line through it. That means all real numbers. If I use interval notation, then I'm going to use parentheses, -infinity, comma, infinity, close parentheses. Now what this means, these parentheses tell me when something is included or not included. Now, since infinity is something that I can't physically touch, it's not technically included. Infinity is not necessarily a specific number that I can count to. So we always use parentheses when we're referring to infinity. And we always go from left to right. So looking at a graph from left to right, negative infinity is over here and positive infinity is on the right side. So we say from negative infinity to positive infinity, there's every x. I can plug it in and it'll give me a y. That's interval notation. The last type we need to talk about is inequality notation, which just says I'm going to go from negative infinity to x to positive infinity. So this is saying x is bigger than all the numbers from negative infinity, and x is smaller than all the numbers to infinity. That just means I'm using every single number from negative infinity to positive infinity. Those three things, these three things, are all saying the exact same thing, but it's important that you know how to write them in all three ways because you'll see them written in all three ways and you need to be able to interpret that. Now, when we talk about the range, you maybe have heard of the pencil test. So this is where you take a pencil like this, let's say, and we're going to run it all the way up this graph. And as long as the graph is only touching at one point at a time, then we're going to have a function. And that's going to be what we're looking for here. So I can go from the bottom all the way to the top, and it's going to touch that line. That means that this function also is all real numbers for the range. So we can do the exact same thing as domain. The only one that changes is this guy, because domain refers to x's, range refers to y's. So instead of negative infinity less than x, it would be less than y less than infinity. The very last thing we need to do is the end behavior. So we'll say as x approaches infinity, what is my function doing? So on the right side of the graph over here, my function is going down, which is towards negative infinity. And as x approaches negative infinity, what is the function doing? So on the left side of my graph, my function is going up towards positive infinity. All right, I would like to do another odd number with you. So let's do number 3 together. So looking at number 3, we are looking at a 4 for the degree and a -1 for the leading coefficient, which means this is going to be an even negative function. So I can expect both ends of my graph to shoot down. Now if I open Desmos back up, let's do my split view here again. And I type in this function, we've got negative x to the 4th plus 4x squared minus 3x minus 2. Here's what my graphic is looking like. Let's pull up a table of values here. Why can't I see more of that table? There we go. Oops. So I want to know what happens. Let's see. I like that table, actually. I don't need any more from that table. So I'm going to redraw that table, and here's my x. Here's my y. And we're looking at -2, 4, -1, 4, 0, -2, 1, -2, and 2, -8. So again, I can go ahead and graph that same thing, right? -2, 4, -1, 4, 0, -2, 1, -2, and 2, -8. 6, 7, 8. Yeah. Okay. Now drawing this one is a little bit more tricky because if we look at this graphic, I've got kind of like a little whoop up here. Let's see if I can get that a little bit better. And then we go down to here, and then we've got like a little divot, but then it bumps right back to here. So our graph looks a little bit something like this. So when we talk about domain, remember I said that pretty much every single polynomial function is going to have a domain that's all real numbers. So I'm going to write that as all real numbers. My interval notation would be -infinity to infinity. And my inequality notation would be -infinity less than x less than infinity. The range here is where things get a little bit different. So if we look here, I said that the range happens from bottom to top. So far so good, right? But then all of a sudden, past this last line is where I don't have any graph. There is no graph up here. So this range has a very specific start and stop point. So the starting point is definitely going to be -infinity. Okay, well, my pen stopped working. There we go. So my starting point is definitely going to be -infinity. So I'm going to start with my interval notation saying we're going to start at -infinity. But I need to know what is this point right here. Well, here's what I'm going to do. I'm going to click on my Desmos, and it's going to highlight it for me. Now, range refers to the y values. So the only thing I care about here is what is the y value saying. And that would be the point -1.57, 6.49. So the only thing that I really care about is this 6.49. So I'm going to go from -infinity to that stopping point of 6.49. And instead of using a parenthesis there, I'm going to use a bracket because that is a real point on this graph. It's a point that I could count to. It would be really ugly to count to, but I can touch it, I can count to it, so I'm going to put a bracket around it. If I wanted to use interval notation, we could definitely write it like this. That is fully acceptable. Or, well, we would have to say less than or equal to. Or we can write it as all of the y's that are smaller than or equal to 6.49. All the y's that are smaller than or equal to 6.49. More often than not, you're going to see this. So I would write it like that way. And last but certainly not least, we just have to do our end behavior, which is going to say as x approaches infinity, my function does what? So as x goes this direction, my function is going down towards -infinity. And as x approaches -infinity, what is my function doing? So as my x's get smaller, my function is going down towards -infinity. I want you to do 2 and 4 on your own, and we'll check back in.